Okay, good afternoon, all. Uh, okay, I welcome you all for this today's session. Due to some technical issues, I have started late. Okay, and now I will take a review within few minutes. In previous session, I have completed the classification of the plain carbon steel. Okay, classification of plain carbon steel along with, and we have learned in that we have learned three types: low carbon steel, medium carbon steel, and high carbon steel. And all these three types of steels, these plain carbon steels, we have discussed with respect to their composition, their properties, and their applications. Okay, in this sequence you have to go. That is, first you have to write the composition, then properties and application. Okay, and try to remember in this sequence only. If you are able to know the composition, you can decide their property, general characteristics, and depending on their properties only, you can identify their application. Now, in today's session, we are going to move towards next part, that is a classification of the alloying elements. And in the previous session only, I have discussed with you that is what is the meaning of alloy steel. Okay, plain carbon steels are alloys of iron and carbon as an alloying element. Only single alloying element, that is nothing but carbon, will be there. That's why they are termed as plain carbon steels. And other alloying elements may be there, but in very negligible amount. Now, if an alloy, okay, alloy, or you can say that the alloy of iron and carbon, it is nothing but steel. And if other alloying elements are there or present in a significant amount, suppose like titanium, zirconium, chromium, molybdenum, silicon, nickel, aluminum, copper, like this number of alloying elements are there. If they are present in the significant amount, then that steels are termed as alloy steels. Okay, now before going to study or start the study of different alloy steels, we will first try to understand what is the effect of these alloying elements on the steel. Okay, when these alloying elements are added in the steel, what changes are going to happen, or what is the effect of that particular alloying element on the properties of steel. Now, before starting that, first we will understand the basic classification of the alloying elements. Okay, generally these alloying elements are classified in two ways. Okay, in this first slide you can see three different types are there. Okay, with respect to these alloying elements are classified in this first slide by considering their relationship with the carbon. Okay, with respect to their relation with the carbon, these alloying elements are classified in three types: as carbide forming elements, then graphitizing elements, and neutral elements. Notice the meaning of carbide forming elements: the alloying elements which when added into the steel, alloying elements which when added into the steel, they combines with the carbon and they form their respective carbides. Suppose you have added chromium, then they will form chromium carbide. Okay, suppose you have added vanadium, they will form vanadium carbide, like that. Whenever alloying element is added, then if suppose it combines with the carbon, if it combines with the carbon and form the respective carbide, then it will come consider under this category carbide forming element. Okay, examples of this carbide forming element are titanium, zirconium, vanadium, niobium, tungsten, molybdenum, chromium, manganese. Okay, these are different examples of this carbide forming elements. Then next type of these alloying elements, depending on their reaction with the carbon or relation with the carbon, next type is graphitizing element. Notice the meaning of graphitization. Okay, whenever suppose you have added one element into the steel, then whichever carbides are already present in that steel, that alloying element will break that carbides. Okay, suppose due to the addition of chromium, chromium carbide is formed, And if you have added small amount of nickel or copper, then it will break that carbide. Okay, it will break the carbide, and due to the breakage of that carbide, what will happen? uh, graphite graphite is nothing but the carbon will get separated. Okay, carbide forming means they will combine with the carbon, and that element will form its respective carbide. And graphitizing element, what they will do, they will break or decompose the existing carbide, and they will separate the carbon in the form of graphite. These elements are classified under or considered under this category, graphitizing elements. And the element which will act as a graphitizing elements are silicon. You can see here examples, I have written some examples: silicon, nickel, copper, aluminum. Okay, these are examples of graphitizing element. Then the third type with respect to its relationship with the carbon is neutral element. Okay, what are the neutral element? Whenever these elements are added in the steel, they neither forms carbides nor causes the graphitization. Okay, means they are not going to form any carbide, or they are not going to break any carbide to get carbon in the form of graphite. Okay, in this neutral category, there is only one element, and it is cobalt. Okay, while writing the chemical formula for cobalt, you have to take care that this O should be small. If you write it in the capital, then it will indicate the carbon monoxide. Okay, please take care of it. uh, this is the name, or you can directly write the name. Cobalt is the only neutral element. Okay, then this is the classification with respect classification of alloy elements with respect to their relation with the carbon. Then these alloy elements are classified in two other types with respect to their effect on temperature intervals in which allotropic forms of iron exists. Okay, in short, I will tell you these uh, alloying elements are classified on the basis of their effect on the critical temperature lines present in the iron carbide equilibrium diagram. Okay, we have discussed various critical lines: A0, A1, A2, A3, A4, then ACM. Different critical temperature lines are there. Then what effect they causes when they are added in the steel, depending on their effect, these alloying elements are classified in two different types, as austenite stabilizer and ferrite stabilizer. Okay, now one by one I will explain it here once, and after that I will show you in the iron carbide equilibrium diagram, or I will explain that they are only austenite stabilizer. Okay, just I will explain it with the help of iron carbide equilibrium diagram. It will help you to understand in easy way. Okay, okay, this is your iron carbide equilibrium diagram. Okay, please see carefully here. Okay, if suppose any alloying element you have added, uh, you know which alloying element is austenite stabilizer. Okay, now here in iron carbide diagram, you can see identifier. This is the austenite phase. This is austenite phase in this region, and below this line, this is A3 temperature line. Below this line, here ferrite is present, some separate ferrite, and ferrite in the form of pearlite, that is the mixture of ferrite plus cementite. Okay, below this temperature line, we will be able to get the ferrite, and above this 727 we will get the austenite. Okay, now when suppose one element is added, and due to addition of it, what will happen? This A3 temperature, here A3 temperature is at 727. This is A3 temperature line. If it falls, okay, here it is this is nothing but your A1 line, you can say that, and it is coinciding with the from this point E A3, A2, A1, all these three lines will coincide. You can say from this point E, it will be A3, A2 or A1. Suppose this, I will term it as A1. From this point up to this is the DF line. It will indicate the your eutectoid temperature. Suppose when you have added one element, you can say the aluminium. Suppose you have added aluminium, then what will happen? This temperature will fall. Eutectoid transformation temperature will decrease, and this A4 temperature, okay, this inclined line, A4 temperature will increase. And what will happen due to this? The stability or area of this austenite phase will increase. Stability of austenite phase will increase. Hence, these alloying elements will be termed as austenite stabilizer. Okay, these are austenite stabilizer. They will increase this loop. Okay, it will get, this loop will get extended. That elements will be termed as austenite stabilizer. And then there are a ferrite stabilizer also. Below this line, we will get the ferrite. And suppose some elements you have added in the steel, then what they will do? They will increase this temperature. Okay, this line, this A1 line or A3 line, you can say that this temperature will increase. It will move in upward direction. Due to that, what will happen? Area of ferrite will increase. Area, or you can say the stability of ferrite phase will increase. Hence, that elements are termed as ferrite stabilizers. Okay, you can say that tungsten, chromium, titanium, these zirconium, vanadium, these are ferrite stabilizer. When you add these elements in the steel, what will happen? This A1, or you can say that A3 temperature will increase, and this A4 temperature will decrease, and a range or stability of ferrite phase will be more. Means you will get ferrite phase. That will be termed as ferrite stabilizer. And if you have added certain elements, and if they are decreasing this temperature, okay, this A1 or A3 temperature will fall, and this A4 temperature will increase. Means area of this austenite phase is more, or stability is more, then that elements will be termed as austenite stabilizer. Now there are certain elements, if you have added beyond the some limit, then what will happen? From room temperature up to the melting point, only a single phase will be there. Suppose only austenite phase is there. From room temperature up to its melting point, if in that particular steel only austenite phase is there, then that steel is termed as austenitic steel. Okay, austenitic steel. As from room temperature up to the melting point, only a one phase present, and that phase is nothing but your austenite. Then it will be termed as austenite, austenitic steel. And if suppose some elements we have added beyond certain limits, like chromium, zirconium, vanadium, these elements we have added uh, beyond certain limits, then what will happen? From room temperature, okay, from room temperature up to melting point, only ferrite phase is there. Only ferrite, that is the alpha phase is there. Then what will happen? Then that steel will be termed as ferritic steel. Okay, so in this way, the alloying elements are classified in these two types. Okay, elements which raises the A4 temperature line and lowers A3 or A1 temperature line, and increases the range of stability of austenite. These are termed as austenite stabilizers. And these elements are nickel, copper, manganese, carbon, nickel, nitrogen. Okay, and then some elements which when added in the steel, they will lower the A4 temperature and raises the A3 or A1 temperature. Hence, they will increase the range of stability of ferrite phase, and these are termed as ferrite stabilizers. Okay, zirconium, one by one I will tell. Titanium, then boron, zirconium, vanadium, niobium, tungsten, molybdenum, chromium, silicon, all these are ferrite stabilizers. Okay, and there are two different type. Wait, the check. Okay, I have added this here. Steels which shows austenitic structure, that is austenite phase from room temperature to its melting point, are termed as austenitic steels. And steels which shows ferritic structure, means only ferrite phase from room temperature up to its melting point, and then these steels are termed as ferritic steels. Okay, austenitic steels and ferritic steels. They may ask you these questions in the multiple choice questions, okay, MCQ questions, or they may ask you in the match the pairs. On the left hand side, they will provide you the steel names, and on the right hand side, they will provide phases. Okay, and you have to choose the correct option. Austenitic steels, only austenite phase from room temperature to the melting point, and ferritic steels, only ferrite phase from room temperature to the melting point. Now, after discussing this, or after understanding the classification of the alloying elements, now we will move towards their effect when they are added into the steels. If you are having any query, let me know. If any query is there, please mention it in the chat box. Am I audible? Please let me know any queries there. Any queries there? Okay, now we will move towards next point. Okay, we will now discuss the effects. Okay, these are effects of alloying elements when they are added into the steel. Wait, let me check whether. Okay. Okay. Now, whenever you add alloying elements into the steel, okay, then they may cause one or more effects. Okay. Now, generally occurring effects I have summarized here in some 6-7 effects. I have summarized here in 2-3 slides. We will discuss one by one. Now, whenever you add alloying elements, they may cause one of this following effect, or some alloying elements may cause many effects. Okay. Now the first effect, whenever you are adding alloying elements into the steel, is formation of the carbides. Okay, already we have discussed in classification of the alloying steels. If it is a carbide forming element, then it will certainly result in the formation of respective carbides. Okay, whenever carbide forming alloying elements are added, they will combine with the carbon present in the steel and they will form the respective carbides. Now, question arises here, what is the effect of this formation of the carbide on the properties of that steel? Okay, as already we are aware about this, whenever carbides are there, okay, whenever certain elements are forming carbides, generally carbides are hard in nature. Okay, they are having very high hardness, and they are having very high resistance to the wear, abrasion, or corrosion, you can say that in short. Okay, means whenever whichever carbides are formed, they are having very high hardness and they are having very good wear resistance or wear good corrosion resistance. Okay, or good abrasion resistance. Okay, means these properties will get improved due to the formation of the carbides. Then other properties like they also increases the resistance to the softening or tempering at elevated temperatures. Elevated temperatures is nothing but the at higher temperature ranges. What will happen? Steel will become due to whenever high temperature surrounding is there, that steel will become soft in nature. That process is termed as tempering or softening. At higher temperature ranges, steel will become soften. Okay, now due to formation of these carbides, what will happen? This resistance to the tempering will be more. That steel will provide more resistance, or it can be used at elevated temperatures for more longer durations. Okay, now generally whichever carbide forming elements are there, they will result in the formation of the carbides. Okay, already we have discussed titanium, zirconium, vanadium. Then Nb is nothing but niobium, and tungsten, molybdenum, chromium, and manganese. I have listed here. These are when they are added in the steel, they will form their carbides. And out of these, the chromium, this is Cr, and vanadium means V. Their carbides means chromium carbides and vanadium carbides. They will give you maximum hardness. Okay, these carbides will give you maximum hardness. Okay, means these two elements, chromium and vanadium, are most effective elements from carbide forming group. This is the first effect. Then the second effect, okay, whenever alloying elements are added in the steel, they may combine with iron present in the steel. As iron is our base metal in the steel, they may combine with the iron. Then they will result in the formation of some intermediate compounds. Okay, they will result in the formation of intermediate compounds. Now some examples I have written here. These intermediate compounds, generally these intermediate compounds increases the brittleness. Okay, means their shock resistance ability of that particular steel, it will get decreased due to the addition of this. Okay, whenever we are adding some alloying elements like nickel, silicon, aluminum, zirconium, they will result in the formation of some intermediate compounds, different complex intermediate compounds like FeCr or Fe3 and W2 like this. This is W nothing but the tungsten. Okay, whenever these kinds of element compounds are formed, what will happen? They will result in the increased brittleness in the material. Brittleness means the shock resistance ability of that particular steel will get decreased. Then the next effect is uh, formation of inclusions. Okay, inclusion is nothing but whenever some alloying elements are added in the steel. Suppose you have added some silicon, aluminum, or manganese, or vanadium. I have mentioned these examples here. You can read it from this. For example, for example, I have added the respective elements. Okay, so suppose aluminum is there. Now this aluminum will react with the oxygen, and it will form the aluminum oxide. Respective oxide they will form, aluminum oxide or titanium oxide or chromium oxide, like this. Different types of oxides will be formed, and they will act as an inclusion in that particular type of steel. Inclusion, or sometimes it will be considered as an impurity only. Different types of oxides they will be, means the formation of intermediate compound and formation of these inclusions, these are these two you can consider as impurities. These are considered as impurities only. Then the next is the effect, lowering of the critical cooling rate. Now, to understand this critical cooling rate, you will understand this term very well after completing your fourth chapter, heat treatment of steel. In that chapter only this critical cooling rate term is there. Now, I will explain it in short way. Uh, whenever cooling rate, critical cooling rate is nothing but whenever cooling rate is there, which will able us to get the maximum hardness in the steel. Okay, maximum possible hardness we can get with this critical cooling rate only. It is the you can say that the critical cooling rate which will give a certain phase. That phase is nothing but martensite. Okay, just what you have to understand here, don't go in the depth. When this critical cooling rate, it will give you the desired structure which will provide you the desired maximum hardness in that steel. And what is the effect of these alloying elements on this critical cooling rate? It will decrease the critical cooling rate. It will decrease the critical cooling rate, means easily you can harden that material. Okay, whenever you add these alloying elements into the steel, easily you can do the hardening of that steel, except the cobalt element. Except cobalt element, if you added any other element, then what is their effect? It will means due to the addition of that alloying elements, you can easily perform the hardening. Okay, you can easily perform the hardening because it decreases the critical cooling rate. So this is the effect of alloying elements on the critical cooling rate. Then effect of alloying elements on the you can say that critical temperatures, like eutectoid temperature. Only eutectoid temperature and eutectoid composition is considered here. Okay, here this point, first we will understand the effect of alloying elements on the eutectoid temperature. Generally, whenever we are adding the any alloying element in the steel, what will be its effect on this eutectoid temperature? Already this we have discussed in the classification point. Okay, austenite stabilizer and ferrite stabilizer. Okay, we have discussed that ferrite stabilizer increases the eutectoid temperature, A1 temperature or A3 temperature. Means whenever you are adding austenite stabilizer, ferrite stabilizer, please read the point number 2. Austenites, ferrite stabilizers, when added into the steel, then what will happen? It will raise or it will increase the eutectoid temperature. And here you can see these are the elements: titanium, molybdenum, silicon, tungsten, chromium. These are ferrite stabilizer. Whenever we are adding ferrite stabilizer into in the steel, then what will happen? They will increase this eutectoid temperature. All these elements are ferrite stabilizer. When they are added in the steel, they will raise or they will increase the eutectoid temperature. And when austenite stabilizers like nickel, manganese, copper are added, then what will happen? Or what will happen here? Then eutectoid temperature will decrease as austenite stability will be more. Okay, elements which are austenite stabilizer, which when added in the steel, they lowers the eutectoid temperature. And elements which are ferrite stabilizer raises or increases the eutectoid temperature. So this is the effect of alloying element on eutectoid temperature. Okay, ferrite stabilizer will increase the eutectoid temperature, and austenite stabilizer will decrease the eutectoid temperature. Then what is the effect of eutectoid composition? 0.8% carbon is our eutectoid composition. Okay, and then if suppose you have added other alloying elements, then almost all alloying elements which when added in the steel, they will decrease the eutectoid composition. And here in the graph, it will indicate that as percentage of other alloying elements is increasing, eutectoid composition is also decreasing. And in this, the most effective element is titanium and molybdenum. With small amount of titanium, your eutectoid composition will fall up to 0.2% carbon. Okay, with small amount of molybdenum, okay, up to suppose 3.5 to 4% carbon, it will decrease up to 0.2%. Sorry, 3.5 to 4% molybdenum, you will get the carbon percentage or your tectoid composition will decrease up to 0.2%. Generalized statement here, you have to remember the effect. Whenever any alloying element is added, generally it will decrease the eutectoid composition. And in case of eutectoid temperatures, ferrite stabilizer will increase the eutectoid temperature and austenite stabilizer will decrease the eutectoid temperature. Then we will move towards the next point. Okay, now this is very important effect, that is solid solution strengthening. Okay, solid solution strengthening, here this effect, solid solution strengthening effect, or you can say that hardening effect of various alloying elements when they are added in the right. It is shown in the diagram. Okay, now I will explain it. Most of the alloying elements are soluble in the ferrite up to some extent. They are soluble in the ferrite, and beyond certain limit, what will happen, they will form a solid solution with when they are added in the steel. Okay, suppose you have added manganese, chromium. Here I have highlighted the list of elements which will form these solid solutions with iron: manganese, chromium, tungsten, molybdenum, vanadium, then titanium. Okay, all these elements, when they are added in the steel, they will result in the formation of a solid solution with the ferrite or with the iron. You can say that they will form a solid solution. Then what is the characteristics or properties of the solid solution? Whenever a solid solution is formed, generally solid solutions are harder and stronger in nature as compared to the pure metal. If any solid solution is there, okay, suppose pure iron and its solid solution with carbon or any other element, you can find that that solid solution will provide you more hardness and more strength. Okay, due to formation of solid solution, what will happen, this will increase the hardness and strength of that particular steel. So this effect will be termed as solid solution strengthening, or the solid solution hardening, or simply hardening. In some books, simply hardening is the word used in this. Now this is the solid solution strengthening or hardening effect. And this hardening effect, in this hardening effect, phosphorus, silicon, manganese, these are most effective. Okay, most effective elements means with their small quantity, they will provide you more hardness, or increasing the hardness value will be more. With very small amount of phosphorus, increasing the hardness will be more. Here on y-axis hardness is plotted, and on x-axis the concentration of alloying elements in the ferrite is plotted. Means this phosphorus and silicon and manganese, these are most effective elements. With their small amount, the strength and hardness of steel will get increased in the more amount, or more change will be there. Then some generalized effects are there after this solid solution strengthening. Okay, due to the addition of alloying elements, the corrosion and oxidation resistance of the that particular steel will increase. Then how this corrosion and oxidation resistance will increase? Suppose, for example, chromium alloying element is added, then this chromium will react with the oxygen and it will form the chromium oxide. and a one thin layer of that chromium oxide will get formed on the surface. Suppose this is the steel, and due to the oxidation, a small layer, very thin layer, suppose this is the layer of chromium oxide. Then what will happen? Due to this layer, thin film, this steel will get protected from the environment. So it will increase the corrosion resistance and oxidation resistance of the steel. Okay, due to formation of some oxides like chromium oxides. So it will increase the corrosion and oxidation resistance. Then due to the formation of carbides, another effect will be on their properties will be like this: the creep strength and fatigue strength of that steel, it will get increased. Okay, more fatigue strength or more creep strength will be there due to the formation of fine carbides. Okay, whenever carbides formations are there and these are very fine in nature, then they will improve the creep strength and fatigue strength of the steel. Okay, then uh, this is the effect of the alloying elements. Whenever you are adding the alloying elements, some phase changes may be there, and due to during this phase changes, some volume changes may be there. Now whenever you are adding the alloying elements, you have to take into consideration these volume changes occurring. Okay, suppose this is the silicon, this round uh, circle. Circle will indicate the silicon element. Okay, and its effect on the volume change. Okay, while choosing the quantity of that alloying element, you have to take this point into consideration. Various elements may be chosen in the proper proportion. Why proper proportion is necessary? If more volume changes are there due to addition of certain elements, then distortion and cracking will be more. Distortion and cracking will be more. And to avoid this distortion and cracking in the elements, you have to choose the proper amount, okay, or proper quantity, and for that you have to consider this also, and this will be considered as volume changes occurring in the particular steel. Okay, due to addition of these elements like silicon, manganese, nickel, chromium, molybdenum, and cobalt. Okay, here most you cannot say that this is the most effective. You have to add the higher percentage. Whenever volume changes are more, suppose this which element here, this is silicon, this is molybdenum, then cobalt, then this one manganese, nickel, this is the chromium. Okay, okay, this is the chromium element. When percentage of chromium is more and more, volume changes are more, means distortion cracking will be more. So you have to control its quantity depending on it by considering the volume changes. Okay, so in this way we have completed this part. uh, Classification of the alloying elements. In this today's session we have finished this classification of the alloying elements based on their relationship with the carbon as carbide forming element, graphitizing element, and neutral element. uh, and also we have considered their classification or discussed this classification based on their effect on the critical temperature lines like A4 or A3 and A1, A3 or A1, as austenite stabilizer and ferrite stabilizer. Then we have discussed what is the meaning of austenitic steel and ferritic steel, and we have discussed the general effects of alloying elements on the properties of steel. General effects are formation of the carbides, then formation of intermediate compounds, formation of inclusions, then lowering of the critical cooling rate. Almost all uh, alloying elements will decrease the critical cooling rate except cobalt. Then effect on eutectoid temperature and eutectoid composition or eutectoid carbon, depending on whether that is austenite stabilizer or ferrite stabilizer, it will change the eutectoid temperature, and almost all alloying elements will lower the eutectoid carbon value. Then the very important effect is solid solution strengthening or hardening. Due to formation of solid solutions, it will result in the better strength and better hardness of the steel. Then due to formation of some oxides like chromium oxides, it will increase the corrosion and oxidation resistance. Then due to formation of some fine carbides like chromium carbide or vanadium carbides, more grip strength or fatigue strength will be provided by that steel. Then while adding, then what will be the volume changes during after addition of these alloying elements in the steel, that you have to understand to control the distortion and cracking during the hardening process. So these are generalized effects when effects of alloying elements when they are added into the steel. So in this way we have completed this session. Please put your roll number in the chat box for your attendance purpose. Please mention your roll number now. And if any query is there, you can mention your query also in the chat box. If you are having any doubt related to this today's session on classification of alloying elements and their effect on the properties of steel, please you can ask the queries or put that query in the chat box. After finishing your or mentioning your roll number in the chat box, immediately you can leave this session. Okay, thank you. Thank you all for attending this today's session on based on effect of alloying element on the properties of steel along with their classification. Thank you very much. Now I'm closing this meeting.